All right, everyone. Let's continue on logical equivalence. So, last time we learned what it means for expressions to be logically equivalent. They have the same truth tables. There's a pretty important special case of this. Sometimes a logical expression is equivalent to something which is always true or always false, and we have special names for these. So, a tautology is a logical expression which is always true, no matter what its inputs are. And, in contrast, a contradiction is always false. So, here's an example. Um, Either I baked bread today, or I did not bake bread today. This is a statement. It's an or kind of statement. We can see our disjunction operator here. And the thing about this statement is that this statement is always true. It's logically equivalent to truth. It's always true, regardless of whether I baked bread today. Because if I did bake bread today, then the first part of the or is true, and if I did not bake bread today, then the second part of the or is true. And remember that either of those being true is enough to make the entire expression true. So if I told you, hey, either I baked bread today or I did not bake bread today, you would say, hey, cool story, Phil. That's not very informative because what you just said is always true, and I don't even know whether you actually baked any bread or not. So let's take a look at another example. So here's another one here. I went for a hike today, and I did not go for a hike today. So unlike the last one, this logical expression, this statement, is always false, regardless of whether I went on a hike or not, because obviously I can't both go on a hike and not go on a hike. We can formalize these two examples with truth tables. So here's a truth table for the first example. Either I baked bread or I did not bake bread. So what I'm going to do is I'm going to form a truth table for not P, and then I'm going to have not P or P. And if I do this truth table, my possibilities are T and F for P. I flip to form the negation. And then when I compute not P or P, well, what I need for that to be true is for either of my two inputs to be true. And guess what? In every row of my truth table, exactly one of my two inputs is true. And so I get all truths on the final column of this truth table. In contrast, if I form the truth table corresponding to the second example, not P and P, this time I'm going to have the same first two columns, but now for the and to be true, I need both of my two inputs to be true, and it's not the case that both of them are true in any of the rows, and so this is false in each case. So these two truth tables show two logical equivalences. One is that P, not P or P, is equivalent to true, and not P and P is equivalent to false. These two logical equivalences are sometimes called laws of the excluded middle. Although you don't have to worry about memorizing that, just remember that not P or P is a tautology, and not P and P is a contradiction. There are a few special logical equivalences that go with tautologies and contradictions, and these equivalences often go under the name elimination rules. So elimination rules say when I can remove a tautology or a contradiction from a statement, or when I'm actually going to only be left with a tautology or contradiction in a statement. That sounds a little funny, so let's go ahead and look at an example. P or F. a contradiction. Let's think this through. If I know that one part of my disjunction operator, or if one of my inputs is false, that must mean that the other input has to be true in order to make the entire expression true. This means that P or F is logically equivalent to just P itself. I can eliminate the F from this expression and be left with just my proposition P. On the other hand, P or true, P or a tautology. In this case, this expression is always true, because even if P is false, the second input, my tautology here, that is true. And that means the entire expression is always going to be true. So this means that in this case, I can actually eliminate P and be left with only the tautology. Similarly, P and F, P and a contradiction, is never ever true because it can't be the case that both of these both of these inputs are true simultaneously because one of them is always false. So this means that P and F is itself a contradiction. The P is eliminated. Similarly, P and true, P and a tautology, that's only true if P itself is true and false otherwise, which means that this is logically equivalent to P, the tautology and the conjunction are eliminated. So we can use these elimination rules to simplify logical expressions involving tautologies and contradictions. So far, we've seen several logical equivalences, but there's a lot more, and importantly, we don't have to always resort to truth tables in order to develop logical equivalences. We can get new logical equivalences from old logical equivalences. And the key insight here is that if two logical expressions, two propositions or compound propositions formed from many operators, if two logical expressions are logically equivalent, then I am always allowed to replace one with another in any logical expression anytime I want to. So let's do an example. We'll jump right in. We have this somewhat complicated logical expression here, P and, parentheses, Q or not P. And what we'd like to do is see what that is logically equivalent to. In order to do this, we are going to do something that looks a lot like a mathematical calculation. And similarly to a mathematical calculation, we're both going to do the steps and justify what those steps are using. So what law or previously known logical equivalence we are invoking in order to know that those steps are valid. So let's go ahead and start. The first thing we'll notice here is that we have an and operator on the outside and an or operator on the inside. So this looks like an opportunity to use a distributive law. So you saw an example of a distributive law in a recent warm-up. So we are going to distribute the and across the or. So our logical equivalence is P and Q. So here that's this P and the first argument of the logical or, P and Q. Then the or goes here, and then P and not P. So, and this is important, I'm going to, on the side of my calculation, I'm going to cite what property I am using. So in this case, I'm using the distributive law in order to justify this first step. Now, I can keep going. So I don't have to do any truth tables. I can actually just keep matching patterns and looking for opportunities to simplify. So in my next lines, I'm just going to write my next logical equivalence right under the previous one. I am going to notice, so my P and Q I'm going to carry down, but I'm going to notice that this P and not P, well, that's a logical contradiction according to the law of the excluded middle. So I can actually just replace that with F, a contradiction. So here I'm going to justify this with the law of the excluded middle. Now I'm almost done. I'm going to do one more line. So for my one more line, I'm going to notice, hey, anything or F or a contradiction. Well, we have elimination rules for that. When I have something or a contradiction, I eliminate the contradiction, and all I'm left with is P and Q. So over here, this is an elimination law. So by following my steps and using a sequence of different logical equivalences, I can simplify logical expressions. This is very similar to algebraic manipulation that you've seen in many math classes before. And just like when I'm doing mathematics, it's very important that I cite the properties that I'm using alongside my calculations. So when I take any kind of mathematical step, it's important that I can cite exactly what property, what known fact, in this case logical equivalence, is allowing me to make that inference. So often in this class, I'm going to refer to this kind of layout as a standard form for calculation. So this is a kind of calculation that we're doing here. So the important components of standard form are that I have a chain of equivalences, or equalities, and each one is justified by a known fact, and there's a justification for each and every step I take. So we're going to see this pattern many, many more times in this class, and one of the things that you're going to practice doing many times is writing calculations in this standard form as a chain of equalities justified in each step.